going back and forth for the past weeks about what I'm supposed to talk about and what should I talk about, and I sort of changed things last night in some sets. And so you've seen and we've all heard about a lot of the physics you can do with Kepler. People have already talked about that, so I'm going to try and go through that a little quickly. But basically, the Kepler mission is there we go, sorry. There we go. Okay. So what I decided to do was sort of give the somewhat standard Kepler talk, which is here's what Kepler does, here's what our results are. But I'm sort of trying to intersperse in places where there might be physics connections, kind of based on our talking yesterday about how these missions should try and make an effort to point out things. And so I think most of these are probably obvious, and I'm sure it's incomplete. Hopefully it's not too wrong, at least what's in there. But this is the Kepler mission goals. Kepler was first kind of conceived by Bill Barucki, who's the PI, in a paper in 1984, Barucki and Summers, where he described looking for transits of extrasolar planets using in this case it wasn't that wide, but using a detector that would allow you to look at a lot of stars. It was 3,000 stars. I figured we'd give you a chance to see something. And the goals of the mission haven't really changed much, especially since the first proposal went to NASA in 1992, I think. It was the fourth time they were proposing. But the goals are basically to find the frequency of terrestrial planets, and so you can read them up there, to characterize the properties of these planets, and to understand how the planets occur around the stars, either singles or multiples or binaries, So the top ones are really the key ones. The discovering terrestrial planets and detecting true Earth analogs is very exciting, but the important thing really is the frequency. If we find one Earth, that would be very exciting, but that's not Kepler's goal. Kepler's goal is to try and put a number on how common or rare they might be. So the design of the mission was such that we should see a lot, and so if we don't detect any, that means something statistically. And that was important going into the design of the mission. So we want to be able to say, if we don't detect any and we really believe the thing's working, then Earth-sized planets in the habitable zones are really rare. So there's a whole bunch of physics tie-ins in those goals, and Dave Charbonneau has a poster out there which has all these on there in much better detail than I've got here. But basically, it's the obvious ones. We basically use Kepler's laws to characterize these planets. The ideas of transits are very, very simple and easy to understand, which is good for me. The other thing I tried to do was to put terms that are somewhat jargony maybe in red. I'm sure I missed a lot, but just things that might trip people up more or less, to a higher or lesser level. We can use the dynamics to decide how far the planet is from its star by measuring the period and using Kepler laws. We can then use the energy balance arguments to say, okay, we know the star is this hot at this temperature, and the planet's here, so how hot is it going to be? And that gets to the sort of definition of what we call habitable zone, which I'll have a little bit more of later. And that, as I started to think about that requires a lot of physics to do that relatively simple equation. You need to know kind of the black body to figure out the temperature and the number of photons you're getting, the energy you're getting. It also has a bunch of assumptions that are at some level most certainly wrong. The simplest one is that all the planets are in circular orbits, and we pretty much assume that, even though we know it's not true for much of our analysis in Kepler, just because it's very hard to do if you don't assume that. It also, you have to assume some planet albedo or reflectivity or emissivity. And you have to assume what happens to the energy when it hits the planet. Is it like the moon, where it's really hot on one side and really cold on the other? Or is it like Venus, where it's the same temperature everywhere, like the Earth, where there's differences? So in order to get what might be the temperature of the planet, you have to really assume something about the atmosphere, and then you start to get into the greenhouse effect. Is there a strong one? Is there none? And that determines really what the temperature is. And also, this is not physics, but the geometry, the idea of transits is very sort of 17th century, and it's very to do with geometry, and people pointed out using Venus to find the size of the solar system. But basically, the transit gives you the relative area of the planet and the star, For the Earth Sun, that's 1 in 12,000, or about 84 parts per million, which are the numbers we throw around. And then the geometry also tells you, because if we're going to see a transit, the planet has to go in front of its star. And if planets or orbits of solar systems or planes of solar systems are randomly aligned, then the probability turns out to be, again, simple geometry, basically the orbital radius over the star radius. And for the Earth Sun, that's about 0.5%. And that assumes, again, eccentricity is 0. And it assumes that solar systems are randomly aligned in the galaxy. And I think everyone believes that's true. There's no evidence that it's not true. But that's a little bit surprising to a lot of people. Well, the galaxy's flat, why aren't they all lined up like that? And so that's something that is assumed in those calculations, but let's say. And finally, there's some statistics, probably brush over, which is basically this idea of the null result. We want to be able to find enough planets such that we find very few or none that mean something. And so there's a binomial distribution there, but basically you want to make sure you can find enough, and that really sets the size of the number of targets you have to look at, given that probability of 0.005 of actually seeing one. So for every one we see, there are something like 200 out there. We see 1 in 200. So that there's some statistics you can get into there. The next. Okay. The next sort of standard Kepler slide is here's Kepler's mission design. People have probably seen this. It's a Schmidt telescope. It's a very basic instrument. It has one instrument. It's got a mirror, a corrector plate up here for the Schmidt optics, and a bunch of CCDs here. And it sits there and it stares at one set of stars. And the design, as I say, was optimized to find this sort of one Earth transit and one Earth-sized transit around a star like the Sun. And the size of the mirror and the field of view of the telescope were set to make that number of expected detections large. And so in order to do that, you need to look at a lot of stars. And there's kind of two fundamental ways to look at a lot of stars. You can look at really faint stars, or you in a narrow field of view, or you can look at relatively bright stars in a wide field of view. Both really kind of money. And Kepler chose the relatively bright wide field of view, and the primary reason behind that is signal and noise. From bright stars, you get more photons, and you can do a better job with a smaller mirror. But that expected signal you need, this 1 part in 12,000, sets your noise level. You need to have that signal bigger than your noise, by hopefully more than 1. And so that sets your noise. You need at least a noise better than 84 parts per million in the time you parabol, which for an Earth transit, it takes the Earth 13 hours to cross the center of the Sun. If it's offset in the solar disk, it's less, of course. And the number we use is the half duration, just for defining things, so that's 6.5 hours. So we said, okay, we want the noise to be less than the signal of the Earth in 6.5 hours. And in this case, we want it to be a factor of 4 or less, so we get a good detection. So that sets our noise at 20 parts per million. And you can then figure out, okay, what does it? On the next slide, you can figure out, okay, given that that's your noise, you can count how many photons you need to get your shot noise or the song noise below that level. And so you can introduce the idea of what this counting noise is. Of course, there are other noise terms, so you actually want it well below that level, because the instrument has noise and CCD can read noise, and so on. You can, the idea of the optics, this sets the size of the optics. You need the size of your aperture, basically, and the field of view sets what you want, sets your focal length of your optics. So you can design this telescope based on essentially that requirement. And that the number of photons you're getting from a star depends on the intrinsic properties of that star, its size and radius, and how far away it is. And so you can talk again about sort of effective temperature as a measure of the star's luminosity or brightness, how many photons you're getting. And then you need to know a little bit of astronomy to say, okay, if I want a star, if I want this many photons, how many stars are there like that, and where do I look for them? And that's kind of the distribution of stars in the galaxy, and the idea of absolute magnitude, or how bright the star, how many photons the star is emitting versus how bright it looks to us because it's far away. So that all sort of comes from the design. So the Kepler's biggest news lately was last February we had our first real big data release, accompanied with a paper listing a bunch of candidates. And so we released the 155,000 light curves for stars for I think it was 134 days worth of data, which sounds like a lot, but we actually at that point had over a year and a half of data, so we were being kind of stingy, but that's what it is. We're arguing about our data release policy now. The interesting thing was all the candidates we found. There were 68 Earth-sized planets in that planet candidates. I'll use the word carefully here. 288 super-Earth, which are defined somewhat arbitrarily. 662 sort of ice giants like Neptune, and 160 like Jupiter. Of all those planets, 54 of them were in their habitable zone of their star by some definition. The smallest were smaller than 54 of them were in their habitable zone. And so this was based on the first 120 odd days of data. So because we need to see generally several transits, these are all relatively short period things. Nominally, it's sort of 1/3 of 130 or whatever, but some are longer because we have 2 transits that are large enough that it's obvious of the planet. So we're not seeing out to the 1-year orbits yet. And we're sort of starting to get to that point now. But we are seeing for cooler stars that have a little bit closer, so we can start to see them. And one of the really interesting things, I think, was that 170 of the stars in this list showed multiple transits. And so we're seeing, transits from multiple planets. So we're seeing different planets in the same solar system aligned enough that we can see them both, or all 3 of them, all 4 of them, or all 5 of them, or 6 of them, or 8 of them. So Kepler's doing a great job. This is from the press release. Again, the physics here is kind of, I think that I underlined that thing Brad about the habitable zone. But basically, it's what do we mean by this? And it's the simple argument is it's thermodynamics would say it's the place where the equilibrium temperature is such that liquid water could be liquid on the surface. It's a very simple definition. There, as everyone probably knows, there are large arguments about what habitable zone means anything. And that makes a lot of assumptions that I'm sure aren't listed here. But first, you're assuming there is a surface. Like Jupiter is a solid surface. And the word habitable, what does that really mean? Well, in this case, it means liquid water. It means it's at that temperature. That's all it means. And then you start thinking, well, really habitable. It can't have just got that temperature yesterday and then be changing tomorrow. It has to have been there for some time. So there's this idea of continuous habitable zone, how long you're sitting in this nice place, and you can see, and that can get you in a little bit to how stars evolve and their temperatures change, and that changes the temperature of the planet. There's the idea of other effects that might keep it from being habitable, such as radiation. One of the things people are thinking about a lot now is planets around M dwarfs. They're cool stars. Their habitable zones are very close in. They're relatively easy to detect because the stars are small, so the transits are bigger. The area of the planet is relatively bigger. But the M stars have a lot of activity and flares, and there are questions about whether those large solar events would cause it not to be a nice place. And I think there are arguments on both sides that would not be that important. And I'm sure and then the other things listed above. You also, in habitability, can get into a little bit of Newton's laws. Someone yesterday mentioned about the escape speed of molecules. So if you have a planet that's very small, you're not going to be able to hold an atmosphere, which means your liquid water is not going to sit on the surface. It's just going to go right away. If it's too large, then you're going to collect a large hydrogen atmosphere during formation, probably if there's hydrogen around, and so you're not going to have a nice surface. So there's the idea of habitability can also include a range of planet sizes. And as Charlie pointed out, this is all sort of very human-centric. This is habitable by things that might be a little bit like us. And then the big caveat is, Earth is outside of our habitable zone in this definition, and Venus is inside, because Earth is too cold unless you have a greenhouse effect. And Venus is okay, I think. But Earth has a 1 bar atmosphere that's nice, and Venus has a 800-degree, 90 bar atmosphere that's not, it's like sulfuric acid, but it's not so nice. So we can't distinguish that at all with this kind of mission. We're just finding something the size of Earth and Venus in approximately the right distance from their star. So this is a sort of a histogram of the planets, and the interesting thing here, I think, is that obviously as a peak of these sort of Neptune-sized things, this drop-off is real. We can detect these things really easily with Kepler. It's spectacular how good the light curves are with these big planets. This drop-off, this is supposed to be a super-Earth, is probably a fair amount of detection limitation. It's biases right now, and we're beating down the noise. These things are smaller, they're harder to detect, so we have a less, we detect fewer of them so far. As we get more data, we expect these histograms to come up. This one will never come up as high as those, even if these are more intrinsically common, because we can't detect most of them because they're small in the storage line. So, but we can estimate those biases and back out how many we think there really are to give us the number we see. The exciting thing that Kepler people like to show because it looks so good is this is the transiting planets before Kepler launched, and I think if I back this up, which I think Sarah said you were actually generating this graph originally, if I back this up, what is it? It's not even 2 years. A year, I think, there'd be none up here. And then there's one, and then there's two, and then a bunch of things. There was a huge explosion of ground-based transits discovered around this time. And then Kepler had their first data release, and now they're called candidates. Because we haven't confirmed all these, that we think there's a high yield in this survey. Between probably 80 to maybe 90% of these things probably are really planets that we can argue at that number. And the important thing is we're pushing down in size primarily, but also out in period. And this is the Kepler's February data release. Now we've really pushed down, and we're getting a fair number of things smaller than the Earth. And we're starting to get out in periods, and you can see this cutoff here is really just a detection cutoff. We can't see small things in long periods yet. We need lots of transits to see them. So this is a graphic put together by Jason Rowe, who's sort of the most brilliant person working on Kepler, I think. He started out as a postdoc and has just done a ton of stuff, and he's a great guy. He worked on MOST, a little bit on Corot. And this is for the February data release, this is a photograph, a picture, a family portrait of all of our planets with realistic star colors and realistic star sizes and realistic planet sizes. And it's really cool. I think this is like, wow, there's a lot of candidates out there. And the sun is shown for comparison, and that's Jupiter there. The Earth is on the sun too. I don't know if you can probably see it on my screen. It's very small, so even Jupiter is fairly small. You can just see the range of sizes of stars we're looking at. I think this is a really cool graphic that was put together. And this is a somewhat more traditional, more boring version of the same thing, which is just the location of where our planets are in an HR diagram. This is from a Howard paper that came out where they're actually trying to estimate, to back out the number of the frequency of these intrinsic planets based on these observations. It's a very paper. But this...
Is there a number
there? There's a lot of disagreement with this number. They limit their discussion to the boxed areas and to specific regions that I actually cut off because I had them on the slide before. Specific period range, I think I'll go up to 50 days. There was 2 papers, and one was 150 and one was 50 days.
Has a plot been made where they try to put the same data on there along with whether or not they fall within that star's habitable zone? Because you have the effective temperature.
Yeah, and that would be show where the habitable ones are.
You could, yeah. I mean, as a data set.
Yeah, I think that's.
Yeah.
Not that I know of. But
okay. I'm sure Jason will be on in a half hour.
Yeah.
He heard us ask.
He did. So what these last things that Caldwell Kepler Candidates is, I was trying to figure out what field of physics is this, and it's really it's classification or stamp collecting or something. But it's important because finding one transiting planet lets you say, oh, there's a transiting planet, and it really people at that point believed that the radial velocity things people were seeing were planets by that time. But seeing a transit, then wow, this really is a thing that's the size and mass of a planet, orbiting a star, not some weird stellar activity. So finding a lot of them lets you start to put them in categories and better define these things. And like finding lots of trans-Neptune objects lets you say, oh, Pluto's not really all that special. It's like a lot of other things. The same thing, we find these new classes of planets that aren't in our solar system, like super Earths, and these things that are in between the size of Earth and ice giants. And it lets you start to compare different predictions from different theories of planet formation and decide whether they're consistent with what you're seeing. And again, it lets you get the frequencies of these numbers of these planets. So it's important that this kind of, having statistically significant samples of these things, which you start to do a lot. So what does Kepler do? It measures, this is a Kepler data for about 300 days of data there. I think it's a little over a year of data, actually. Figure out from the scale there. And this is a giant planet, and you can see the red dashed marks there show it's a short period planet, 4.1 days, show the transits, and they're really obvious in the light curve. And having worked on ground-based transit searches, when we saw things like this, it was like, oh, why did we waste all this time on the ground? But having that kind of precision lets you really model these stars in detail and start to get out the shape of this curve, tells you about the limb darkening on the star, and really lets you know the inclination angle. Is it going through the center of the star, or what's the impact parameter on the star? If you can get, it does show it better here on my screen. If you can get radial velocity measurements and photometry, you can do joint modeling and actually get better star parameters than you can get from spectroscopy or just from any of this alone. You can get the density of the star sort of independently based because the photometry and the radial velocity tell you about the property. You can solve the equations and the property of things. So we've got a bunch of giant planets, like Orbital giant planet, where we've got a radial velocity, a really nice solution. This is using two different telescopes. The different colors are the blue and the red are two different fibers on this Nordic optical telescope in the Canary Islands, and the green is the HET habitable telescope. And they agree really nicely, and this gives us a mass and also a density from those planets. So the other things modeling can do is you can start to if the data are really good, which they are for some of the bright stars, you can start to get more details of what's going on in the system rather than just seeing it in this picture. It's basically a flat line, and then it transits, and then nothing happens. Sorry, I should explain. The top curve is the unfolded light curve spread out over time. The bottom curve is phased at the period of the planet. The red is the transit. The green is the occultation if one was there. And so we use this as a metric. If it was an eclipsing binary, you would see a second green dip, and that's the size of that is an indicator of whether or not it's a planet or binary. So that's the sort of setup, and then there's some numbers describing various things. But if you yeah.
I'm not sure what the graph on the right is.
Oh, sorry, I didn't say anything there. I'm doing all this jargon. So this is a radial velocity plot of the phase to the period of this transit, and
the star.
So the phase is it's the radial velocity of the star. Yeah. So it's the reflex motion of the star. The amplitude here is sort of it's not set to 0 because it was in two different telescopes, but it's sort of plus or minus 100 meters per second. It's a pretty big signal relative to what people can do nowadays.
Is that also on the same Kepler website?
That this one is not yet. This is in a publication that I'm supposed to be writing. Not being very effective at getting out yet, but there are this candidate is released. The photometry has been released through all the candidates through order 2 is 130 days, and I'm trying to remember for the candidates we give them a KOI, Kepler Object of Interest, for whatever reason number. I'm trying to remember offhand the number of this one. I think I think it's 130. I actually cut it off. I think it's 135, but I have to look. But it's the photometry, at least out through 134 there, are released, so you can see, how soon you were keeping all this extra stuff.
Is the use of both the Kepler method in photometry and also the radial velocity curve being done to confirm aspects of the system and to be able to do the calculations more rigorously in some way? Because it seems like you have what you need from the planet's occultation data.
So that's and a few slides back, I switched, and that first slide was planets before 2009 and candidates after, and that's this huge problem we're facing now. Is that to get this many radial velocity points on this relatively boring short period giant planet took a lot of nights and a lot of time, and there's no possible way we can do that for the 1,200 candidates, especially the small ones that aren't 100 meter per second amplitudes, which are actually the interesting ones. And these were relatively small telescopes. EGT is not, but the North Optical Telescope is relatively small, so the dimmer stars, the smaller planets require Keck. That's basically the only game in town right now. And Keck time is very expensive and very sought after, and people aren't going to give up lots of Keck time to confirm short period giant planets like this. So we're really going through a change in paradigm of announcing. The old school way was, here's a transit, here's radial velocity. You model possible confusion sources and say, okay, this is a planet that's confirmed. And you put a check mark. We can't do that with all these candidates, so we're trying to come up with ways of using either just the photometry and then maybe a good classification spectra to say, okay, the likelihood that there's a false positive that would look like this is very small, and the likelihood that there's a planet in this phase space is much, much larger than that, and use some sort of validation arguments that it's most likely that this is a planet instead of a background binary. And if you do that 1,200 times, then you can say, okay, this list of 1,200 is 95% planets reliable, and we're sort of trying to make arguments like that now. Yes.
It seems like that's the only way you can get at the eccentricity of the orbit, is with radial velocity curve. So are they going to follow up the ones that seem most potentially Earth-like?
We are, yeah. I mean, and again, the problem is, Keck can't really detect radial velocities from the Earth, especially in long periods. Yeah. And so all we can do is put upper limits. And one of the most powerful, I don't really have anything about it here, is things we're doing is doing high spatial resolution imaging around these sources and essentially seeing if there are any background stars there. And if you can rule out background stars to some small patch in the sky around this target, then you can say, okay, the probability that there's one in this little tiny patch that's at the right magnitude to give us the signal can be very small. And so it doesn't get to the eccentricity question. You can start to say, okay, there's very little probability that this is anything but a transit we're seeing. And that's really all we're going to be able to do, I think, for the really most interesting candidates. A lot of the radial velocity surveys tend to look at stars that are kind of brighter than 10th magnitude. All of our stars are, the majority of our candidates are 14th magnitude, I think, so just a little bit of this. The other cool thing when you start to see, again, this is kind of for short period planets, in this case it's very massive planets, you can model the phase curve of the light. So this is a plot, a folded light curve on the top here of a planet. It's a massive planet around a massive star, actually in a very short period orbit, so things are moving very quickly. It's an A star. And the transits are near phase 0 and 1, and they've been removed from this plot. And the occultation when this planet is behind the star is at phase 0.5, and it's also been removed. And they would all be off scale on this plot if they were still shown here. The point of this work was to show what you can see around there. And so the individual points are Kepler 30-minute data points, which is our standard sampling mode. And the dark black points are just bit-in averages of those points. And you can see this nice phase curve. And what this is a combination of three effects. And there's a reflected light effect in their model down here in this bottom curve. There's a reflected light effect, which is essentially the phase of this planet, like the phase of the moon. as it goes behind the star, you see the full face. As it comes in front, you see a new planet. The blue effect, which is this double hump, is the ellipsoidal variation, like in binary stars, because this planet is massive enough, it's raising tides on its star, and the star is not round, it's not spherical, it's football shaped, whatever it is, teardrop shaped. And as different amounts of area of the star present their face to us, the star gets brighter and dimmer. And so that gives you the mass of the planet, the amplitude of that, just like in binary stars, the amplitude of that effect tells you the mass of the planet. And then the coolest thing in here, I think, is this red signal, which is very small. You can actually sort of see that the hump here, sorry, on the not very good left and right, on the left is higher than the hump on the right. And this is Doppler beaming. As the planet's orbiting the star, it's tugging the star around. It's like the radial velocity measurements. And we're actually seeing the Doppler beaming as the star moves toward us. It gets a little brighter. As it moves away, it gets a little dimmer. And that's because it's a short period, massive planet, so things are moving very fast. So you can actually you can see these effects and model them and with realistic precision decide, oh, this is really happening here. And
I don't understand the difference between this and radial velocity.
It's the relativistic beaming effect of a light source moving toward you or away from you. So you're getting more photons as opposed to getting more evolution photons. And so the point of this work, which is a paper that's in the press now, is that if you didn't have transits and occultations, if this thing was just transiting, you could still detect this planet and you could still determine its mass without any radial velocity. So this is a very cool application of modeling in sort of a specialized corner, because it has to be a massive planet in a very short period orbit. But it's kind of cool. So the physics here that's kind of new, again, this modeling lets you talk about Newton's law. We talked about that already. The E&M you get from the radial velocity. We talked about this yesterday. I think you can use E&M to describe Doppler shift and what you're seeing. The light curve modeling, if I go back to, I'm sure everyone's seen this, the bottoms of these transits aren't flat. The planet's supposed to be a dark disk moving across the star. The model, and actually the model we use to search for them, is essentially a flat bottom pulse. But the stars aren't uniformly bright, and so you can maybe introduce the idea of limb darkening, which is the fact that you're looking at the star and it's the radiation coming to you from the edge of the star is going through more of the star's atmosphere than from the center of the star. And finally, this idea of the special relativity, and it's an example of special relativity in action. I think one of the coolest things, and it was really, I didn't expect it, was the number of multiple planet systems that Kepler's seeing. This is from a paper that Dave Latham put out. The top plot is a radius of planet versus period plot on the log scale. And the red dots are the single things where we've only seen a single planet. The blue dots are things where we've seen a multiple planet, more than one planet around the same star. And this is the same plot, just zoomed in this region of short periods and on a new scale here. It's just a different view of the same thing. The amazing thing, I think, was that these multiple transiting planet systems are so common. If you think about the probability of alignment of the solar systems, they have to be very well lined up for us to see transits of both of these things. And if we were looking at our solar system from far away, when you saw a transit of Earth, I think you only have something like a 10% chance of seeing a transit of Venus, which is near the lines of nodes of the two, because the orbits they're pretty well aligned, but they're not aligned enough. So these are some sort of remarkably flat systems, and we're seeing a lot of them. And it's close. This paper talks more about it, but it's close to the level that the number we're seeing kind of implies that every single one of these must be a multiple because of with some misalignment, depending on whether you say they're actually forced to be aligned really precisely or you allow some variation. They're very common, which is very cool. The other thing you can notice, probably especially in this plot, is that there aren't very many multiples with large planets in relatively short period orbits up here. And that's probably not too surprising in hindsight, in the sense that these really Jupiter-mass planets probably couldn't conform that close to their star because there's not enough mass in the disk and that close in to get there. So they had to have come in from the outside, and when Jupiter comes in like a big bowling ball, it's going to scatter everything away. So there could be planets way outside that we're not seeing yet, but they're not in close. And so that's, it makes sense from that kind of argument.
Those reasonable dynamics are like
yeah, after 51 Peg was discovered, well, actually before, but pointed out after 51 Peg was discovered, there were several theoretical descriptions of planet migration that explain, oh yeah, of course you expect to see Jupiter in 3.5 day period orbits. And so that there's this, and then actually the problem became, well, they should just keep on migrating and go right into the star, and so they come up with some mechanism to stop them. And so they're losing angular momentum to the disk as they form, and they just come barreling in. So it makes sense. The most exciting system we had at the time was this Kepler 11 system, which has been announced and confirmed. And there are six transiting planets that we can actually see transits of. Basically, all sort of around the orbit of Mercury for the biggest one. This was a Nature cover article, which was very cool for Kepler. The interesting thing, one of the really good things about multiple systems is that these planets, especially in these, you can see these things are packed in pretty close, and in fact they're packed about as close as you can get them and have them be dynamically stable. And so you couldn't add too many more planets in there and have this thing be stable. And so these planets are interacting. There are a lot of these, and a lot of the multiples are in orbits that are near resonances, and so they're interacting pretty strongly. So what that means is that their orbits are changing on timescales of Kepler's observation, timescales of years, by amounts that are large. So this plot over here is for this Kepler 11 system. It's the observed minus predicted transit time. So we see the transit, we know the period, and we say, okay, we should see another one. And the transits are arriving, these are in minutes. So the transits are arriving, in this case, sort of 10 minutes early and late. Up there, it's even more. And so these are measurable relatively easily to see these things interacting. And this isn't the best example. There's some other ones I couldn't pick up, but the top one you can sort of see the yellow points have this sort of W shape, and the red points have this sort of M shape. These two planets are interacting with each other. As one speeds up, as one arrives earlier in its transit, the other one is slowing down and arriving later. And so that interaction confirms right away that these are both around the same star. If you believe that those are sort of anti-correlated, and you can use statistical to show it, then these things are really, they're not 3 stars in the line of sight that happen to have planets. These are really around the same star. And also the amplitude of the interaction tells you the masses of these things. And in this case, we were able to confirm that several of these have planetary masses. There were a couple like this guy at the bottom that isn't interacting strong enough to put limits on. But you can, again, without radial velocity, in the case of these multiples interacting, you can say these have planetary masses. This is a plot from a paper by Eric Ford, I believe. Yeah, and this is a plot of the MAD, which is the median or the mean absolute deviation, some measure of the variation of the transit timing versus the uncertainty. And what this is telling you is that what are statistically significant measures of transit time? So this is all of our candidates, and in the simplest thing, kind of anything above this line has a transit timing variation greater than the uncertainty. And so if you're well above this line, which is the log plot, there's a bunch of points that are, it's a really significant transit timing variation. And the red points on here are the known multiples, and the little crosses are the single transits. There's a bunch of single transits with transit timing variation. And what that's telling us is that there's something else in that system that's perturbing that orbit. And as we start to observe these for longer, you can see the period and amplitude of that perturbation and get an idea what the massive period of that perturbing thing are, even though it's not transiting. So it's
another planet.
So there's another planet or maybe a star in some of the cases. Yeah. So it lets us see, essentially see other planets there, detect other planets there. It's very cool. And finally, knowing the mass and radius of these planets, which is kind of what we're really after, the first order lets you get the density, which is what we want to know. Is it rocky, or is it a gas giant or ice giant? And this is it's cartoony, stylized from the press release. But basically, if you know the mass and radius, the degree of radius and mass of the planet, you can put it on this diagram, and you can draw theoretical curves or model curves of where compositions of different types of composition fall in this diagram. And you can say, in this case, Kepler 10b was the first. We say, for people would disagree, we say it was the first, indisputably rocky planet, because the uncertainties in the mass of this Corot planet were much larger, and you could put other compositions through there. But essentially, these planets are definitely not made out of mostly hydrogen. In this case, for Kepler 10b, its composition is essentially rocky. It's not iron, it's not water. So we can really start to say what these planets are if we do kind of planetary geology, which is a very cool thing. So the physics, I think we've already talked a little bit about this. I'm not sure how much this multiple planets you can get into interaction in the free body and more problems and dynamics. The idea of orbital resonances. A lot of the multiples we're seeing are very near resonances, period ratios of 2 to 1 or 3 to 2, and those interact strongly with each other, and you can get the idea of how these essentially are beating against each other. It's very cool, and the fact that that we're seeing a lot of these that are really have very small mutual inclinations. It implies something about the angular momentum of the disk in which these things came from, or some damping factor that's putting them into the same plane. They seem to be more aligned than you would expect, looking at our solar system, for instance. And again, I mentioned you can sort of get at the geophysics of these planets and start to talk about what they're actually made of. And we hopefully go into more on that. And that again has kind of a lot of assumptions, because it's hard to distinguish, a big iron core with a fluffy exterior from a smaller iron core with a more rocky exterior. So there are assumptions, and you can kind of really only say about the average composition of this thing is not mostly hydrogen or not mostly water. And again, then there's these weird definitions of what do you mean by a rocky planet or a water world or ice giant or gas giant. This I'm going to really give short shrift to, because I didn't run out of time and I don't know enough about it. But one of the cool things that Kepler's doing, in fact, there was a great talk at the AAS by Ron Gilliland about the Astro seismology results from Kepler. And he had a plot, a pie chart of the number of papers, and the number of papers from Kepler data on Astro seismology in this pie chart was 75% of the pie chart. And the number of papers on exoplanets was this little slice of like 25%, and it made all the exoplanets important. So there's amazing things coming out of the astroseismology, and what astroseismology in a nutshell is looking at the oscillations of stars. Things aren't showing up here that I thought that they were on, but whatever. This is again the HR diagram, and the little hash marks. This is from Jørgen Christensen Dalsgaard in Denmark, who's sort of the world's leading experts in this, are different regions of instability in the HR diagram and different oscillation regions. This one here, which you can't really see, it's yellow on yellow, is sort of sun-like stars, and that's what we're really aiming for. But there are other variable stars and things that oscillate, and astroseismology is essentially measuring the oscillations of stars to get at what they're made out of and what their interiors are and what their structure is. And it's relatively simple in the sense that you have this big sphere of gas, and it's oscillating in the different kind of modes that a sphere can oscillate in. And you can measure, all we can measure is the brightness, but as the star oscillates, the brightness changes and you do Fourier transforms of them, and you see these peaks, and you can measure the frequencies and determine what modes it's operating in, how many nodes it has, and that tells you the frequencies of these different modes, these low mode number ones, have long wavelengths that essentially probe the entire star, so you actually get information about the interior of the star. These higher frequency ones, higher mode number ones, tell you more about the surface. And so you can actually, surprisingly to me, you can get incredibly accurate measurements of the radius, the density, the mass, and the age of the star from these different measurements, just by measuring the brightness and being able to see these different oscillations. For solar-like stars, the oscillations are very small, and before Kepler and Corot, there were only a small number that were actually measured besides the sun. But Kepler's finding there's tons of them, and I guess for bigger stars, the oscillation amplitudes are bigger, and you can do a lot more. Sorry. Should have done that earlier. So there's just the different oscillation areas. So there are a whole bunch of other sort of astroseismology related things studying variable stars. For the upper right here, this is some typical giant stars, subgiant and red and blue giants, because these things are bigger, their oscillation periods are longer and they have bigger amplitudes, and so they're easier to detect, but also you can learn more about them because they have bigger signals. So there's a paper just recently about actually measuring the different oscillations from different depths of some giants, and actually letting you decide what the core is, whether the core is helium, whether it's helium burning or hydrogen shell burning. So it lets you put information, determine where things are on the HR diagram in ways that were previously unobservable, just by measuring these different oscillations and the different relative amplitudes and frequencies of the deep oscillations versus the shallow ones. Variable star work, probably besides its really good precision, the most useful thing about Kepler is it's essentially continuous observations. So you're not missing things. This is RLI rating. This was put up by someone in the seismology group who had made those observations on the top, which are ground-based observations that were a multi-site campaign over a very long time and a huge effort. And that's what RLI looked like, and they did a great job and an amazing analysis, and we're able to learn a lot about this oscillating star. And this is the Kepler data from the first sort of year, and it's just it's having continuous data, just like Fourier said, really helps a lot. I mean, you can see a lot that you can't see, and they're actually starting to understand what these oscillations are, and there's smaller oscillations on top of there than the amplitude of the signal. So there's just a ton of sort of variable star work that we're getting. The bottom plot here is a erupting nova that's changing by many magnitudes. It's quiet one wall here, and it has these large eruptions. And by looking continuously with Kepler, you see the whole thing, which is really nice. Before people had seen, there's a bright outburst, and you watch it for a while from the ground and do what you could. So it's just that you come in there. The physics there's tons of physics in the astroseismology, of course. Thermodynamics, the idea of these stellar oscillations, this ball of gas, and the sound speed is what's controlling these oscillations at frequencies. And so that gets you to the pressure and density and equation of state of what's in the star. The idea of what's driving these oscillations is in the sun, they're thought to be driven by convection, sort of random jiggling, exciting these modes, which are then quite unstable, and they go on. So it's the idea of convection in the sun. If you have oscillation, but if you have a star that's not convective, you wouldn't expect to see these as much. So radiative transport versus convective transport. So energy transport, oscillations and waves, obviously. Spherical harmonics, another example of spherical harmonics, and how they may be to explain them. And these interacting stars, I think we talked about yesterday, we can get into the idea of type of forces and even sort of getting Roche limits of these things. And the orbital period, like for the interacting cataclysmic fires, the orbital period sets some of the time scales of these things you're seeing in the light curves. So you can get out from the frequencies of various waves of what's going on in there. So that's kind of all the science I have. This is the boring mission chart, which is Kepler's timeline. We should advance this a little bit more. So we're sort of here. Kepler's nominally scheduled to stop observing in November of 2012, and then we have a kind of a year of data analysis after that. We're actively trying to get it extended now and it's likely that it's probably going to go through the senior review process this year, starting in February, so next year, beginning of the year. It's working very well. It's not a lot of excitement here. The red little asterisks are safe mode, where something went wrong and the spacecraft said, oh, something's wrong, and it's safe mode, and it stops taking data and starts spinning and connects itself. So we had some early on, and then we had a couple in the winter of the first year of observations that sort of fall into here. And then we went for nearly a year without one, and then we had some more in the last winter, so we decided that the winter doesn't like winter for some reason, but it's been doing well since then. The only hardware failure we've had is, I didn't even show it, the focal plane is made up of 21 modules laid out in a 5x5 grid with the corners missing, and each module is 2 CCDs, and one of the modules died actually back in, let's see, that little sort of gold diamond above my hand there. One of the modules died, and so we don't get data from that part of the focal plane. But the good news is we rotate the spacecraft 90 degrees every 90 days or so, so we still see those stars that were in that patch of the sky 3/4 of the time. So it's bad because we're not seeing it continuously, but we're still at least seeing them, and we can still detect things going on there, except when they occur when we're and that's really about it. I have the Kepler picture and quote, of course, which is really appropriate for this conference.